Welcome everybody to this new week of the Big Data for Engineers course. So what's on the menu today? We are going to continue on the massive parallel processing part. So we discovered MapReduce in 2 weeks ago, and that we finished, before the Easter break, and that we finished last week. And then we looked into a next generation of massive parallel processing that took it to the next level with a more generic approach. So for example, in MapReduce, it was only key value pairs, but in Spark can be any value, including pairs, of course, but not just pairs. In MapReduce, it has to be map, shuffle, reduce, but in Spark can be any sequence of transformations in any way you like. Yeah, so it's a more generic system. All right, so I have a few questions that I would like to ask you to make sure that you've been following, and then we'll continue with the Spark material. All right, so let me share my screen. There we go. So here's the first question. So MapReduce works with key value pairs, but our input can be in many different forms: text, binary, tables, JSON, CSV, and so on. So how is the input converted to key value pairs then? Do we use each block ID as a key and the block as values? Do we hit the input with a hammer until it fits into the key value model? Is there a natural way to convert each input format into key value pairs? For example, in HBase, the row ID acts as a key and the row as a value, or we use each file name as a key and the content as a value. So we have a majority, and the majority is correct. Congratulations. So indeed, there is a natural way to do it, but of course, it depends on the format. If you have a relational database, the primary key can act as the row ID, and so on and so on. The block ID, no, we are not using the block IDs for the keys. This is not based on the blocks, and that would be too big because a block would be enormous. And the file names also not. All right. Okay. Here's another question. We introduced first, before the Easter break, what's known as the first version of MapReduce. And then we saw very quickly, because as I said, I reduced the material in order to keep it on the high level. So I just want to know what issues did Yarn solve? You know, Yarn, yet another resource negotiator. So what did it bring to MapReduce to actually add Yarn to manage resources? So it basically fixed issues. So is it that map slots and reduce slots are statically assigned, so they are often idle, which doesn't fully use cluster resources? When a MapReduce split spans over 2 HDFS blocks, there's a massive drop in performance because data must be streamed from another data node over the network. Is there a bottleneck on the job tracker, which has to do with both scheduling and monitoring, jack of all trades, master of none? Or is it that map slots and reduce slots are statically assigned before the job starts, which may lead to a suboptimal number of reuses? I think multiple answers are possible, if I set it up correctly. Let's start looking at your answers. So there's a majority for 3 of them, except one that is less popular. Okay, so you are correct, indeed. All of that is solved, right? All of these problems except the one with reading from another data node that doesn't go away. Right? If we saw that there is a slight impedance mismatch between blocks and splits in MapReduce, because a block is cut in a bitwise, but a split is separated record-wise. So you might have a few more bits from the splits that go to another block, and that's not solved by yarn at all. It's still something that persists. All right. And here's a third one. What is an RDD? Is it a resilient distributed data set? Is it a recoverable distributed data set? Is it a recoverable dividable data set? Or is it a resilient dividable data set? All right, so that's something I assume most of you know by heart. Resilient distributed data set. Distributed because it's partitioned, just like the key values in MapReduce, right? So it's partitioned and spread all over the cluster. And resilience comes from the fact that even if we lose it, we can rebuild it. Right? So whenever we lose data, we just reconstruct it by recomputing the RDD, right? So it's intermediate data and reconstructed if we lose it. All right. Okay, so that's enough. These are enough questions now. And let me go back to the slides. And this even works again, because in the meantime, while you were answering the questions, I managed to fix it. All right. So this is the big thing about Spark, right? We generalized the whole computation model from just map and reduce to a whole structure that is called the DAG. Does anybody remember what DAG means in the lecture hall or on the Zoom chat? What is a DAG?
Directed acyclic graph.
Exactly, directed because these are directed arrows, right? There's a flow of the data. And acyclic because there is never arrows that come back to the original point. It always flows, but it never comes back to the same node again. This is what it means to be acyclic. And you know, we computer scientists are geeks, so we like to invent new terminology, and this is why we just say DAG instead of directed acyclic graph, because it's easier. All right, but this is a DAG. Okay, so where did we leave last time? I gave you a whole menu of transformation. It's like being to the restaurant and you can pick your starter, you can pick your entree, you can pick your dessert, and so on and so on. So there's a whole menu of transformations and actions and even input formats that you can have. But we saw that there's different kinds of transformations. There are the transformations like filter, like map, like simple map, that kind of are vertical and there is not too much spaghetti in the middle, right? So I started explaining to you how we implement physically the computations that use transformations that don't have spaghetti. So it's those that have, you know, kind of a vertical structure. What does it mean? That's called the narrow dependency. It means that if I want to compute that value right there, all I need is that value right here. I don't need to know about the other values. So you see, there are kind of these compartments. And of course, when you have these sort of compartments that every value here only depends narrowly on the input, just on that, that's great because you can spread it all over the cluster. So you see, you can do some computations on one machine, then separately on another machine, and so on. And this is how you get tasks, right? So you can have tasks just like we had map tasks and reduce tasks. We split the computation of the transformation in tasks. All right. And then it works exactly like in MapReduce. Like within a task, there is a sequential execution of the mapping or filter or whatever function there is in the transformation. Within the same slot, there is a sequential handling of the tasks, and across the slots, this is all done in parallel. There is another thing that we saw, because you notice this right there. We saw that if you have a succession of several transformations, one after the other, and all of these transformations are like this, they are in a row, then we can kind of squeeze together the transformations and we can compute, in that case, 3 transformations at the same time while not communicating between the machines. There is no shuffling anywhere here. You see, every machine computes locally 3 transformations on a single partition of the input. And we do this in parallel and across the tasks for the entire input data. But this only works if the transformation is like that. Otherwise, it doesn't work anymore. Right? So I will explain to you, of course, how that goes when there is transformations that have the spaghetti. But before that, I also want to repeat to make very clear, again, what I said. Within a task, the execution is sequential. Within a slot that corresponds to a computer CPU core, there is also sequential execution. It's first this task, then this task, but across the slots. This is all done in parallel. So this, and this is all done at the same time, right? So the slots are working in parallel. And I went into even more details about what the slots are because we looked at the containers in the Yarn, and now we know that what a slot is actually a CPU core right there, together with a bit of memory. And we saw that it might be that several slots, several cores even share the memory, right? It's just that it's more efficient to do it that way. We could also have, as we will see, one core has its memory, a core has its memory, but here we just have 2 cores together that share a memory, right? And this is called an executor. All right. So in Yarn, an executor is a container. So the terminology in Yarn is container, and Spark calls it an executor. Right? And an executor in that case has 2 slots, but it can be 1 slot, it can be 5 slots. It's any number of slots you want, but in that case 2. Then another executor with 2 slots. So in total here we have 4 slots that executes this in parallel. But again, all we can do so far is narrow dependencies, right? If there is no spaghetti in there. But of course, in the data, there will be spaghetti. Now, we have a bit of control. We can control a few things. For example, you can choose, if you run a Spark job, how many executors you want. Do you want 5? Do you want 10? Do you want 20? You say. So there is this command line that is called Spark submits. It's something you type on your command line. It's one way of using Spark. And then you have some compiled version of a Java program that basically contains whatever it's supposed to do in Spark. And then you have this parameter right there that's --num-executors. And here I say, okay, I want 42 executors. So there's going to be 42 of these, right? 42 executors. I can also control the amount of memory here. Executor memory, 5 gigabytes. So it means that in every executor here, 5 gigabytes, 5 gigabytes, 5 gigabytes for every executor. I can also control the number of cores that I have in each executor with executor cores 2. In that case, I say I want 2, right? So you see number of executors, number of cores per executor, memory per executor, and I can do it all at the same time. I can say I want 42 executors, 2 cores per executor, and 3 gigabytes of memory per executor. How many slots do I have in that case? How many tasks can I execute in parallel here? Anybody?
84.
84, exactly, because you need to multiply these things, right? 42 executors, but there is 2 slots, 2 cores in each executor. Very, very good. So you're following. Okay. So don't be scared because in the exercises, we are not actually going to use Spark submit and well, you can, maybe there will be a few exercises like that. But in practice, we use Jupyter notebooks. It's so much easier, right? And with PySpark and so on, so you can just type your queries directly in the Jupyter notebook without worrying about that. But for people who want more complex jobs and that have a lot more complexity, then this is the way they will do it. They will compile some cool program that does the transformations and the actions and so on and so on. And then they submit it to Spark via the command line by controlling executors, cores, and memory. All right. Okay. Let's now get to the spaghetti, right? It's not lunch yet, but if we were already hungry or some, but all right. This is a huge spaghetti here that's called the white dependency. How do I see that? Well, it's visible that there's a spaghetti, of course, here, but it means that this value right there depends on this, on this, on this, and on this. So I basically need the whole input to compute that value. So obviously, you can no longer partition it so easily and execute it in parallel. That doesn't work. What will we need to do with that spaghetti? How do we implement that spaghetti? What is it called? It's It's called the same as in MapReduce.
Shuffle.
Yeah, shuffling, exactly. We need to shuffle. And the way it works is that that's the end. Maybe there were other transformations above there that were nicely narrow dependency, but then we have to shuffle. So here we stop the computation. So this is intermediate output issued by the previous slots who computed the task. So that's the output of the previous tasks. And then this goes over the network. This is shuffled around across the machines and so on. And then we have a new inputs for the next tasks that again are done potentially in parallel if there's narrow dependencies again. This is called a new stage. Remember that we call this a stage when we group like these several transformations together. So it means that we have to start a new stage that was a previous stage, then there's shuffling and we start a new stage. In MapReduce, there were two stages, the map stage, the reduce stage, but in that case, there can be more. Here's an example with three stages. So in that case, I have one transformation that is narrow dependency, so I can squeeze it together in the same stage. Here I have one transformation that is wide dependency, so I need to stop stage one and shuffle it around. Then I have stage two. Stage two again, then there's a wide dependency, so I need to shuffle again. You see, I cannot squeeze transformations together right there. Then I shuffle, and then stage three with again here two transformations squeezed together because that's a narrow dependency. Right?
The question is why there are multiple columns for a task?
What do you call columns? Here, what do you call a column?
A line of arrows.
A line of arrows. Do you mean this?
Yes.
Okay. Let me explain that with an analogy with MapReduce. In MapReduce, we saw that a map task consists in executing the map function on every input key value. Right? And this is done sequentially. So I have a split that has, let's say, 10,000 key values. I take the first key value, I execute the map function. I take the second key value, I execute the map function. I take the third key value, I execute the map function, and so on until I reach the end with 10,000. Then I'm done with my task. What's going on here is the same, is that I take my first, it's not going to be a key value always, right? Maybe it's just a value because we saw in Spark, it doesn't have to be a key value, but I basically pick the first value of my RDD, of my split of my RDD, and then I invoke the function that is in the transformation. Maybe it's a filter function, maybe it's a map function, whatever function is there. It's the equivalent of the map function. And then I call the function for the first transformation, and then I immediately called again the function corresponding to my second transformation, right? So I basically chain my function calls, but I do it just for one value of the inputs. I can do it because of the narrow dependency, remember? So I take one value, I execute the chain of the transformation functions to get the output. Then I go to the second value in my partition, and again invoke the function of the first transformation, invoke the function of the second transformation, and then get output. And this goes sequentially. So this is really just a for loop. It's an iteration over every single value that there is in my input partition. Right? Does it make sense?
Yes.
Right. Perfect. Okay. So stages. And of course, we saw that we can have two input RDDs. It was discussed on Mattermost, I remember. So for example, we might have a join here. So what's going to happen? The left side of the join might come from some RDD that was generated with these transformations that was done in a stage. The right part of the join, the right RDD, might come from stage two, another sequence of transformation. And here we need to do a double shuffling, right? So we need to both shuffle what comes from the left RDD and we need to shuffle what comes from the right RDD, right? All of that goes here. Then we have pairs of values, one from the left, one from the right, and then we executed the join. And then here it's again a simple shuffle where we just have one input RDD. You have a question?
Does a stage consist only of narrow dependencies?
Yes, by definition. The reason is that you can only squeeze together the transformations if there's only narrow dependencies here. As soon as you have a wide dependency, you have to end the stage and shuffle. Right? So as soon as you have a wide dependency, you are forced to shuffle. All right, does it make sense?
Yes.
All right, so here's now how to remember these terms. We have a transformation, right? You can apply transformation, but this is a logical concept. You can squeeze several transformations into a stage if there are narrow dependencies. Then what happens is that the stage is executed by splitting across slots and across tasks, right? So it's divided in tasks, and the tasks are executed in parallel and sequentially within each slot. And then a sequence of stages, so the stages are basically executed one after each other, and then that's a whole job, right? So you just need to understand that there's horizontal splitting here of the stages when you spread it all over the cluster, and there's vertical splitting when you consider that a stage has several transformations. Do not be confused, because this is a logical thing. This is on the logical abstract level. This is a physical thing, that you physically execute the stage by splitting it into tasks. Okay? We have other questions?
Yes, it's on the last slide. Where is the narrow dependency in stage 3?
There is none. Here we don't even have any transformation. So what happens? We have this joint transformation that is a wide dependency, followed by another transformation that has a wide dependency. So in that case, we are just unlucky. We have to shuffle before and we have to shuffle after. So here we didn't squeeze anything, because that's just, yeah. So what's happening here is just the computation of the join. Right? We shuffled the join data, and here we compute the join algorithm, but that's it. That's the only thing that happens in there. There is no narrow dependency transformation happening whatsoever, right? No more questions? All right, perfect. Okay, here's now a few tricks. We're almost done with the general performance. So sometimes it can be inefficient, because as I said, you trigger a computation when you pull the string right there with an action, and then that triggers the computations. Then you might pull the string right here, trigger an action, and then it computes all over again. Then you might pull the string right here, it's an action, then it triggers the computation again. But now you saw we did 3 times the same thing, because here we computed that 3 times. So how can we improve that? Well, that's easy. We can just say, okay, please persist that RDD. It means we pin the RDD in here and keep the computation. So it means that when we pull the string here, so maybe the first time we compute all of that and pin it here. Then the second time, we just reuse what is pinned here without the need to recompute that. And the third time, we again directly use that. So this is called persisting an RDD. It can be persisted in memory, it can be persisted on disk if you're really afraid of losing the data. But this is pretty much it. So you see, this is the first way that you can optimize things by pinning the values of an RDD in place in the machines, so that you don't need to recompute the same things all over again. Okay, there's another thing you can optimize. Sometimes you can avoid a wide dependency if you smartly pre-partition the data. It means that if you spread it over machines in a smart way, for example, if you're about to group your data, but if before grouping your data, you already make sure that all the values in the same group are always on the same machine before you actually start applying the transformation, then you no longer have the wide dependency problem, because you have all you need to compute a value on the same machine. This is called pre-partitioning. So if it's pre-partitioned and the data is already such that you don't need to read across machines, then there's no shuffling needed anymore. So what it means is that if we pre-partition the data in a smart way, it's a bit advanced, right? So I'm not going to the details of how to do that. But if we reorder and regroup the data in here and we pre-partition, we can here completely avoid the shuffling on that side. It means there's going to be shuffle from here, but here you can basically stay on the same machines here by kind of also squeezing them together just with this additional incoming shuffle. All right, so that's another way. So you see there's plenty of techniques that you can use in order to make your computations faster, right? Okay, Any questions so far? No questions? All right, let me continue then. I don't know if you observed, but using Spark in that way with the RDDs, transformations, actions, and so on, is quite a low level. Right? If you let's compare it to SQL, for example, when we were using PostgreSQL in the first week of the lecture, and all you needed to do is tap a few lines, and there you go, you have your data, the results of your query, right? So SQL was super easy, and it was meant to be easy. But now we have to write Python code with PySpark in order to read the data somewhere and manually say, okay, I want to use this transformation and that transformation, and then I want to do this in this and that way. It's very complicated and low level. In fact, it breaks data independence because it forces the user of Spark to do things that they shouldn't be doing as an end user of a data querying system, right? So for this reason, there was an improvement that was made a bit later in Spark that's called the data frames, which is another way than RDDs to compute, to store intermediate data. You might have, who already heard the word data frame somewhere? Can you please raise your hands in the lecture hall or in the Zoom chat?
So several
people.
Yeah.
Okay, very good. Well, actually, it's a buzzword. It's kind of has become a buzzword in data science, probably because of the pandas library in Python that grew in popularity, which is kind of the way of manipulating relational tables, but without SQL. Instead, you use a data frame API. So it's a lower level than SQL, but sharing a bit of the relational model with SQL.
There's a question in the chat. I feel like we discussed data frames before in class as a form of tables, but this is different.
No, it's the same. Now, yeah, I just forgot for a moment that we actually did look at data frames already in data modeling. Yeah. So data frames are when we validated JSON and we had a pattern in the JSON data, and we were able to visualize it as nicely drawn tables, except that we can also nest data. We can have arrays in objects, which gave this more generic way than tables. Yeah. So yeah, I just skipped my mind for a moment. So basically, there's two reasons why you should have heard of data frames. One, because of the buzz with pandas in Python, and second, because we actually looked at it a few weeks ago in the data modeling lecture. Thank you for reminding me of that. It's actually the reason why we looked at it into the data modeling lecture, because we were going to use it in Spark, and here we are. All right. So if you use RDDs and you want to start processing JSON, what's going to happen when Spark doesn't understand JSON? At least RDDs do not understand JSON. So what you need to do with RDDs is you need to read the data, for example, that can come from a text file, and then you need to apply your transformations like this, or filter, map, reduce by key, blah, blah, blah. And then at the end, you have an action, right? So this is typically something you can do in a Jupyter notebook, for example. So this is with text. So with text, it's just strings. So you manipulate strings with functions that manipulate strings, right, in Python. The problem is that if you have a data set in JSON, for example, that is JSON lines, there is one JSON object on every line, then it becomes cumbersome because you have to do it yourself. Spark doesn't know about JSON, so you have in Python to use that function parse JSON. So that's called the lambda, right? The way you pass your function to a filter. So that's your filtering function. Sorry, that's a typo here. It should be a map. So you map every string to a JSON object, which in Python is called a dictionary, right? So you basically parse the line of JSON to a Python dictionary, and then you get an RDD of dictionaries. And then again, in Python, you can use the Python syntax to access the dictionary. So here you look up a key here and you filter for the places where the value associated with the key is 0, and then you map more and so on, right? But you see that it's quite complex because Spark wasn't designed for JSON. So it really pushes the burden of having to do all of that, parsing JSON and so on, explicitly in Python, right? So this is where data frames are actually useful. VID is that one possible way that you can have your RDD, it's an RDD, can be an RDD of anything, can have just a sequence of values. Well, you can say that the values in your RDD are always the row of a relational table, right? So I have one row, one row, one row, one row. So what is a collection of rows? Well, it's a table, or in that case, a data frame, because we are more generic, right? So a data frame can be seen as an RDD of rows. So again, one single value in the RDD is a row like that, with the attributes and the values for one row. If you take the whole RDD, then you have a whole table, a whole data frame, right? And the idea is that it can be stored very efficiently, because the way that the data frames are going to be stored by Spark is going to be column by column. It's a bit shredded like that. So all the values in a column are going to be stored together, and then it allows a few optimizations. An example of optimizations is that Spark might realize that there are columns that are not even needed in the queries anywhere. Then it can even drop the columns completely and get rid of them, right, proactively. So what that means also is that if you have an RDD that you just read from JSON, it's going to take a lot of space in memory. Why? Because the keys are going to be repeated every time. In every single dictionary or JSON object, you always store the keys and the keys and the keys all over again. So it takes a lot of memory. But if you have a data frame, all of the rows have the same keys, right? So you only need to store the values. The keys are just stored once. It's a schema. That's the data frame schema, right, that we looked at in the previous lecture. So what you actually store in your data frame, in the physical data frame, is just the values without the keys. So it actually is more compact. It takes less memory. In fact, this is a direct, we can put it in as an analogy when we converted JSON to Parquet, right? In JSON, it takes more space because the keys are repeated all over the place. In Parquet, we have a schema, we validated it against a schema, and then we have the values without the keys stored in the file. So it's like JSON and Parquet, right? The raw Spark with an RDD and a data frame. Okay. And the super cool thing about data frames, and that's actually the best part, is that with the data frame API, you can read a JSON file as a data frame. So what's going to happen here is that Spark is going to automatically infer the schema from the data. It's going to look at all the data and it's going to guess the schema. It will notice that there is always the same key, that it's always the same time, and so on. And if necessary, it will hit it with a hammer to make it fit into a schema. I'll come back to that. But basically, it infers a schema and it creates a data frame. We can give it a name here. Let's call it data set. And the super cool part is that now that we have a data frame, which looks like a table, we can use SQL. Here it is, you know, SQL that we polished at the beginning of the lecture in our brush up with PostgreSQL. We also have SQL in Spark. It's called Spark SQL. So you see, it was worth learning SQL if you didn't already know it, because now I can directly invoke on my data frame. You see, it's no longer an RDD, now it's a data frame, .SQL, and here, select from, where, order by, and so on, just as a SQL query that I can put in there, and then I can call my action on the data frame. You see how cool that is? We can directly invoke SQL now. This is so much easier than having to write manually in Python the transformations. What's even better than that is that in the Python, in the Jupyter notebooks, it's even possible to hide all of that and to just write the SQL in a Jupyter notebook cell. All you need to do is write the SQL. There is a %% SQL magic that you will discover, similar to PostgreSQL. And all you need to do is type the SQL. So you will see it's night and day with RDDs compared to data frames. So what I want you to feel as an intuition, as part of this lecture, is that it's much, much, much easier to use data frames and use SQL to query data frames than it is to use RDDs and have to write a lot of lines of code in order to manually manipulate the RDDs. All right. So this is it. That's called Spark SQL. It's very close to PostgreSQL. There is a SQL standard, but it's again like the Swiss German dialects, right? There's Zurich, Auschwitzerdeutsch, Baseldeutsch, Bahndeutsch, Walliserdeutsch, Empli and Brüff, all of these words that can differ from canton to canton and from town to town. Well, it's the same with SQL, right? We have the Postgres SQL, we have Spark SQL. They are kind of like each other, but with small differences. But still, the look and feel is the same, so you really will not need a lot of efforts to adapt. All right? Okay. So let me talk again about what happens right there when we do this read. So here it's read JSON, but there's also read CSV and so on. Here's a CSV file. Let's assume we have plenty of CSV files stored on HDFS or on S3. If I read them as data frame, Spark will automatically build the data frame right there that you can then manipulate with SQL. Yeah.
But with JSON, we have trees.
Absolutely. But do you remember that trees mean nestedness, right? And when we have nested data, we saw how data frames support that. Do you remember in the data modeling lecture, I showed you how you have, when you have arrays and objects, that is the tree structure, you can actually draw your data frame in a way that you can have this nested structure. So the nestedness is absolutely no problem if you have nested JSON. The real problem, and this is something you're right about, the real problem is if your JSON is not valid or cannot be validated because the trees are too far apart from each other. You might have a messy collection of JSON objects that are trees that don't have the same schema. This is where data frames stop working nicely, right? And this is what we'll fix in the next few weeks, right? So to summarize, data frames are more generic than tables. They also support nested values, nested objects, nested arrays, but they need a schema. You need a data frame schema. So this is why when you read JSON, you need a schema to validate your JSON, and then that gives you a data frame, and then you can go ahead and use it with SQL. Right. Is there another question?
Yes. So transformations to data frames are applied only through Spark SQL code. For example, we don't use the RDD transformation like map or filter or other transformations.
You can, because some people are geeks, right? And I'm a geek, and sometimes I like to have fun, right? So there are people who, they're not happy with SQL for some reason. They don't like that it's so much simpler, and they still want to do transformations. Well, it's possible. That's the good news. So you also have transformations that you can invoke on data frames. It's not exactly the same list as the RDD transformations. This is really a separate list of data frame transformations. The syntax is slightly different. You see there's this weird way of passing the criterion and so on. There's ask, desk, and so on. So it's a bit low level, right? It's not as intuitive as SQL, but there is a way. So if you really, 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 really don't want to use SQL and you really want to write low-level transformations on data frame, you can, like this. This is how it looks like. All right. Does it help? Does it answer your question?
So it's like pandas in Python with data frame methods?
Yeah, that's pretty much what it is. It's very similar to pandas, except that pandas would be local to your laptop, right? And here it's a similar API, but on a cluster, right? And so the discussion of whether you prefer to use the transformations like this with the pandas API or the pandas-like API, or use SQL, well, as a database educator or teacher, I want to make you understand that this is better because it has there's many reasons why this is better. You're more productive, it's more compact, it's a high-level language, and so on. So there's 50 years of experience that show that using SQL is better. However, there is also this API that is another way of doing that. Do not understand me wrong. I'm not saying this is useless. I'm not saying this is useless. I'm just saying it's not meant normally for the end user. This is more meant for people who want to write programs and want more control about what is done. But the end user, the data scientist querying their data in a company, normally this is the way to do it, using SQL. But for some reason, Pandas grew in popularity so much that a lot of people just use the Pandas API, but yeah, it's not necessarily optimal. It's not necessarily the best recommended way to do that. Okay, are there any other questions? Anything else to clarify? Right? Okay, so we have data frames, we have SQL. So Spark automatically validates. So here it reads the CSV file and it automatically sees that this is always an integer and this is always a Boolean. For JSON, Spark is also smart. It will automatically recognize here that foo is an integer and bar is a Boolean, right? So this is automatic schema inference. It doesn't always work, and I will show later that it has its problems when it doesn't work, but sometimes it works. So in that case, it works, and this is the data frame you get. Right. I'll come back to the nested data frames again later, right? But here I assume flat JSON. All right, so this I explained. And now what about the types of data frames? Well, that's the good news. We already took care of that a few weeks ago, right? So the sort of types that we have in Spark data frames are very, very similar to the types that we've had with JSON or JSON schema, XML schema, and so on when we validate our data. Because guess what? We have numbers, we have strings, Boolean, binary, dates, timestamp, and so on, and we have arrays and objects, right? Arrays and objects where objects can exist as struct or maps, but we discussed that a bit, right? So basically, there's absolutely nothing new in there. The type system of the data frames is just the same that we've seen a few weeks ago, very similar to the JSON type system. And here is yet another table. I already drew one a few weeks ago. Sorry, coughing a bit. I already showed you a correspondence table a few weeks ago between data frames, Spark data frames, JSONic, JSOUND, XML schema, JSON schema, and so on. So here I'm doing one with data frames, Java types, and Python types, right? It's just another example. And you see that again, it's just like the Swiss German dialects. It's just different names, right? But for example, you might have in Java int, right? But in data frames, in Spark data frames, this is called an integer type. In Python, that would be int or long, right? Well, I think in the latest, it has changed a bit. In the latest version of Python, it's just int with unlimited precision, right? You can see, for example, that date types corresponds in Java to a SQL date, and in Python to date point date, right? Okay, so this is the correspondence table. But really, I'm throwing that at you, but what I'm saying here is there is absolutely nothing new because all of that is what we did a few weeks ago. So the columns in your data frames can have all of these types, and there's even complex types because you can have arrays and objects. And I showed you the visual, how to draw it nicely as nice rectangles, you know, the rectangular view of a data frame in the previous lecture. All right. So just before we go to the break, we can read JSON with automatic schema inference. Parquet, we've seen it. That's going to be much faster because guess what? We don't need to infer any schema. There's already a schema in there. So Parquet is going to be much, much, much faster than JSON. And that's why I showed you how you can convert, or the TA showed you how you can convert JSON to Parquet. This is much faster. You can also read CSV, you can read text. Of course, it's going to be more boring as a data frame if you read text. JDBC is if you connect to a relational database, because yes, you can connect to PostgreSQL and access it as a data frame in Spark. And then there's many others, but then you need this format function and you put the format as a string there, avro, and so on and so on. And people can add more and more and more and more as they figure it out. So you see, there's plenty of different data formats, but always, it is as a data frame that we are going to manipulate it, meaning we can use Spark SQL in order to manipulate it, right? Which brings us to our break. So you deserve the 10 minutes to rest your brain a bit. And then we'll finish on Spark, and then I'll tell you a few things about the high levels in massive parallel processing. All right, so see you in 10 minutes. Bye.